The warning came at 2:47 in the morning, and most people were asleep. That's not unusual for the Mid-South. It's almost the rule. A tornado warning system designed around flat, open plains, long sight lines, and afternoon storm cells is now watching a different sky entirely. The geography it was built for is no longer where the killing happens, and the storms didn't announce the change. They just moved. The deadliest tornado outbreaks of the last decade didn't happen in Kansas or Oklahoma. They happened in Mississippi, Tennessee, and Alabama. Mostly after midnight, mostly in places where the houses are older, the basements are almost non-existent, and the radar coverage has gaps the size of counties. That's not bad luck. That's a structural mismatch between where we built our defenses and where the threat actually lives now. Tornado Alley, the name, the map, the whole mental model, has been quietly relocating for 40 years. The question is where it's going, and why the new ground is so much harder to survive. Tornado Alley wasn't discovered, it was constructed. Meteorologists in the 1950s and 60s started mapping where tornadoes concentrated, and a clear shape emerged, a corridor running roughly from northern Texas up through Oklahoma, Kansas, and Nebraska, with the western edge trimmed by the Rockies and the eastern edge somewhere around the Missouri-Mississippi line. They gave it a name, and the name became a fact. It became what people meant when they thought about tornadoes. The geography that created it is real, and it's worth understanding, because the same geography is what made it survivable. The Great Plains sit at the intersection of three air masses: cold, dry air sliding off the Rockies from the northwest, warm, moist air pumping north from the Gulf, and a dry line, a sharp boundary where the two meet. When those ingredients stack in the right order, the atmosphere becomes unstable fast and visibly. The thunderstorms that produce tornadoes on the plains tend to be discrete, isolated, photogenic supercells. They form in the afternoon. They track northeast across open flat ground with almost no trees to block radar beams and no hills to confuse the airflow. Storm chasers can follow them for hours. The warning times, on a good day, can stretch past 20 minutes. That predictability is the piece most people don't credit. The plains didn't just happen to have tornadoes, they had tornadoes in a format that detection technology and warning systems could be designed around. The whole infrastructure of American tornado readiness was built to match that specific recipe. The plains are still producing tornadoes, the recipe hasn't been revoked. So what exactly is changing? Here's what's changing. The data shows it clearly, and it has been showing it for decades. Quietly, in tornado frequency maps that researchers kept updating, and almost nobody in the public conversation stopped to read carefully. When you plot where American tornadoes actually touch down, year by year, across 4 decades, a pattern emerges that has no innocent explanation. The dots are moving east, not randomly, not noisily, systematically. Meteorologists call it a shift in tornado climatology. That phrase undersells it. Some studies tracking tornado occurrence from 1980 onward put the eastward creep at roughly 50 miles per decade. Do the math. That's approximately 200 miles of geographic drift since Ronald Reagan's first term. The center of American tornado activity, the statistical heart of it, has been slowly sliding off the plains and toward a completely different region. Not a blip, not a bad decade. A trend line that has held across administrations, across El Niño cycles, across every argument about whether this was real. And here's where the data gets genuinely difficult to dismiss. The plains haven't gone quiet. Kansas is still producing tornadoes. Oklahoma is still producing tornadoes. The raw totals in the classic tornado alley aren't collapsing. What's increasing, faster, more steeply, is activity to the east and southeast, which means the plains recipe alone can't explain what's happening. If it were just the same system, the same ingredients, the same geography, the frequency would stay anchored where it always was. It isn't. Something else is feeding tornadoes in places the old model never had to account for. So what exactly is moving the needle? The jet stream is the answer. Not all of it, but the spine of it. The polar jet stream is a ribbon of fast-moving air in the upper atmosphere, and it acts as the organizing rail for storm systems across the continent. Where it dips south, cold air plunges. Where it lifts north, warm air surges to meet it. The collision zone between those two air masses is where supercells ignite. For most of the 20th century, that collision happened with remarkable consistency over the Central Plains. The jet sat in roughly the right position, the right number of times, to make Kansas and Oklahoma the factory floor of American tornadoes. But the jet stream is not fixed, it meanders. And the research tracking it over the last 4 decades shows a persistent eastward and southward bias in its winter and spring positioning. The trough, the southward dip that drags cold air down from Canada, is spending more time over the Mississippi Valley and the southeast than it once did. That shift is being amplified by something happening at the Arctic. As sea ice retreats and the pole warms faster than the tropics, the temperature gradient that gives the jet its speed is weakening. A slower, wavier jet stream wobbles more, dips farther south, and holds its position longer over the wrong places. And the lower atmosphere is changing underneath it. Gulf of Mexico moisture is reaching farther north. Earlier in the year, the warm, humid air that tornado-producing supercells feed on is no longer seasonally restricted to the same old delivery window. Which brings us to something that would have seemed almost absurd to a meteorologist in 1975. Warming winters now give the southeast dangerous tornado setups in December and January. December, when no one on the plains would even think to watch the sky for a funnel cloud. The plains shift is no longer a statistical mystery. The jet is running a different track. The Gulf is supplying different fuel. The cold-warm collision is happening in a different zip code. That's the mechanism. But what it unlocks, in terms of raw human danger, is a different question entirely. Because the ground the tornado system is moving onto is not like the plains, not even close. The ground is the whole story. Because what moves onto a flat open Kansas wheat field and what moves onto the ridgelines of Tennessee or the pine corridors of Mississippi are meteorologically the same animal. But they do not kill the same way. Start with what you can see. On the Great Plains, a tornado gives itself away. The sky is open, the horizon is 20 miles out. The land is flat as a table. A funnel drops, and it is visible the moment it forms. A dark column against the sky, often tracking parallel to a road, watched by dozens of people with cameras and half an hour to decide where to go. That visibility is not a minor advantage. It is the whole ballgame. Now put that same tornado in a hollow in eastern Tennessee, or a pine forest in southern Mississippi. The ridges block your sight lines. The canopy closes overhead. The tornado is there. It is rotating. It is on the ground. It is moving. And you cannot see it until it is literally tearing through the tree line a few hundred yards away. Seconds, not minutes. The terrain amplifies this. Valleys funnel debris. Ridges accelerate wind in ways flat ground never would. A hillside that looks like shelter from above is a trap from inside, which raises the question the geography forces. Does anything compensate for it? Sirens, weather radios, the shelter infrastructure. Do those systems close the gap? The landscape opens. Because until that question is answered, the same tornado, the same wind speed, the same path length, reliably kills more people here than it does on the plains. The ground itself is part of the death toll. The answer, when you actually look at the data, is no. The systems don't close the gap. In many places across the Mid-South, they barely dent it. Start with the physical infrastructure. The Great Plains built a shelter culture over generations. Storm cellars dug under farmhouses, community shelters anchored in school gymnasiums, a reflex for going underground when the sky turns green. That culture took decades of repeated visible destruction to build. The Southeast never had the same forcing function, so it never built the same response. Mississippi sits at the sharpest end of this. It has one of the highest concentrations of mobile homes in the entire country. And mobile homes offer almost no protection against even a weak tornado. An EF1 winds under 110 miles per hour, will dismantle a manufactured structure the same way it peels a cardboard box. At the same time, Mississippi has one of the lowest rates of storm shelter ownership anywhere in the nation. The two facts together aren't a coincidence. They're a compounding vulnerability. The most fragile housing stock, the least backup. Outdoor warning sirens were designed for people already outside. Weather radios require someone to be awake and listening. Neither system solves the problem that's coming. Because most of these tornadoes strike at night, which opens a harder question. What does a night tornado do to a population that isn't watching the sky? One asleep in structures that won't survive it, in communities where the shelter doesn't exist. The infrastructure gap isn't a feeling, it's measurable. And the measurement is ugly. Most people is asleep between midnight and 6 a.m. That's not an insight, it's a biological fact. But in the Southeast, it's also a death sentence waiting on the weather, because that's exactly when a disproportionate share of the region's tornadoes arrive. A 2019 study pulled the mortality data and found something that should have reshaped national policy. Nighttime tornadoes are 2.5 times more likely to be fatal than daytime ones, not 50% more likely. 2.5 times, the same storm, the same wind speed, the same track. And at night it kills at more than double the rate. The variable isn't the tornado, it's whether the people in its path are conscious and aware that it's coming. Now overlay that multiplier on a map of where tornado activity has been growing, the Southeast. The exact region where outbreaks increasingly concentrate. The exact region where nighttime strikes are most common, where mobile home density is highest and where community shelters are thinnest on the ground. The 2.5 multiplier isn't randomly distributed across the country. It lands hardest where the tornado belt has been moving toward for 40 years. Outdoor sirens don't wake people through walls and windows. A weather radio requires someone to already be awake. Phone alerts depend on cell towers that storms knock out. Every layer of the warning system assumes some version of an alert person. And nighttime removes that assumption entirely. The night tornado mortality gap isn't a gap in meteorology. It's a gap in everything that happens after the forecast is made. The warning system wasn't designed for any of that. It was designed for the plains, for flat, open ground where radar can see a storm from 60 miles out, where a siren mounted on a water tower carries across fields with nothing to absorb it, where a tornado in July moves at a predictable pace across a landscape with room to watch it coming. That's the environment the infrastructure was built around. The Southeast is the opposite of that environment in almost every relevant way. Hills and ridgelines create radar shadow zones, pockets of terrain that block the low-level scans that catch tornadoes in their earliest stages. Storms in the Southeast move faster, sometimes dramatically faster, than plain storms, and faster movement compresses the margin between detection and impact. The average tornado warning lead time in the Southeast runs shorter than on the plains, not because meteorologists are less skilled, because the physics of the terrain and storm motion leave them less time to work with. A warning issued 4 minutes before impact is a warning. Getting to shelter in 4 minutes at 2 in the morning in a mobile home with no basement nearby is a different problem entirely. And for a substantial share of the population in the new tornado belt, the question of whether a warning arrives at all, at night, when towers go down and sirens don't penetrate walls, is genuinely open. Which raises the harder question: does anyone have a plan to close this gap before the next outbreak arrives? The plan exists, in pieces. Wireless emergency alerts that bypass cell towers entirely. NOAA weather radio with battery backup in every shelter-designated building. Hardened warning infrastructure built around the actual terrain, not the plains template it was borrowed from. Community shelter programs in counties where mobile homes still outnumber basements by 20 to 1. None of this is science fiction. Several of these tools already exist and work in the places that have deployed them. The gap isn't knowledge. The gap is will, money, and the political attention that usually arrives only after a catastrophic enough death toll makes inaction impossible to defend. And here is the full shape of what's happened, from the beginning. 40 years ago, the plains absorbed these storms. Sparsely populated, open terrain, daytime peaks. The geography itself softened the toll. Now the center of gravity has shifted into the Mid-South, where mobile homes outnumber storm shelters by a factor of 10 in some counties, where ridgelines funnel wind into valleys without warning, and where a tornado at 2 in the morning in February is not an anomaly. It is the new pattern. The death rate per tornado in this region runs roughly twice what it does on the plains. Infrastructure built for a different threat, warning culture calibrated to a different season, emergency systems sized for a different frequency. All of it is facing a mismatch that is already showing up in the fatality counts. The data exists. The trajectory is not ambiguous. What follows depends entirely on whether the investment in shelters, sirens, and public education moves as fast as the storms themselves have. And it keeps growing every season we treat Tornado Alley as a place we already know.